Welcome to the video lecture on basic differentiation rules and rates of change. In a previous lecture, we talked about how to calculate a derivative by using the limit definition of the derivative. In this lecture, we're going to learn some shortcut differentiation rules that will save us a lot of time in finding derivatives. Unfortunately, we can only use these shortcuts if the functions that we're dealing with fit the rules of our formulas. So if we don't have a function that fits the rules, then we're going to have to fall back on our limit definition of the derivative. So let's start with our most basic rule, and that's the derivative of a constant function. So let's suppose that a function f of x is equal to c. We're going to derive the derivative of this constant function by falling back on that limit definition of the derivative. So that says that f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now since this function is the constant function, it returns the value of c no matter what our input happens to be. So when we go to simplify this limit definition and we go to evaluate what f of x plus delta x is, it doesn't matter that the input is x plus delta x. This function is always going to give us c back. So this value for f of x plus delta x will just be c, no matter what the input is. Similarly, if I want to know what f of x is, again, it doesn't matter what the input is, this function is always c. So f of x will also be c. So we get in the numerator c minus c, which goes to 0, and 0 divided by something that's small is still going to be 0, regardless of our delta x. So the limit of a constant is that constant right back again. So we just get 0 for this derivative. So here's our first shortcut rule. And this is a slightly different notation. The derivative of any constant c with respect to x is equal to 0. Okay, so the derivative of a constant is always 0. Now let's make our function slightly more complicated. This is going to be the function of the form x to the n. So these are power rules. So what we're going to do to figure out what this power rule is we're going to just basically look at some examples of things we already know. So let's suppose that our function is just a constant. Then we just derived that that derivative is going to be 0. Now let's talk about what happens if the function is just a plain old x. What would be the derivative of that? Well, since x is a linear function with a slope of 1, and a derivative is the slope of the tangent line, then the tangent line to this linear function would be the line itself. Therefore, the slope of the tangent line would be the same as the slope of this line, which we know is 1. So the derivative of x must be 1. Now, how would we find the derivative of x squared? Well, in that case, if you didn't know what it was, you'd have to fall back on that limit definition. So if we wanted to find the derivative of x squared, then we'd have to find the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And in this case, our function is the squaring function. So if our input is x plus delta x, then this f of x plus delta x would become x plus delta x quantity squared. We just square that input. And f of x would then just be x squared. Now to simplify that, we're going to go ahead and FOIL out our quantity squared here. So that would give me an x squared plus a 2x delta x plus a delta x squared minus that x squared. And those x squareds cancel out. And that leaves me with terms in the numerator that only have delta x's. So if I factor out the delta x from each of these two terms, I'm going to be left with a 2x plus a delta x. And that delta x that we pulled out now can cancel the one in the bottom. And it's at this point that we're ready to plug in our 0 for delta x. So just this term right here goes to 0, which means this is going to become just 2x. So it turns out that the derivative of x squared is 2x. Now I'm not going to do it for the next one, but you can see that the process would be exactly the same. If this was the x cubed function, you would just change these to cubes, and your work would be slightly different, but a very similar process. It turns out that the derivative of x cubed is 3x squared, and the derivative of x to the fourth is 4x cubed. And we could keep going here, but what we're trying to develop is a pattern. So what if this was just any x to the n? What would its derivative over here need to be? So let's look at the pattern. On the left-hand side, we have these powers of x. This is x to the first, second, third, fourth, and there's no x on this constant term, but it's implied to be like an x to the 0, since x to the 0 is just 1. So what you'll notice is the coefficients on this side of our derivative correspond to those original powers. So if the power over here is an n, then the coefficient of our derivative will now be n. So in other words, that power gets brought down out front. And then what happens to that power? Well, in each case, the power went down by 1. It went from 4 down to 3, 3 down to 2, 2 down to 1, etc. So over here in our derivative, we would still have an x left over, but its new power would be 1 less. So this is called the power rule. It's probably our most used rule, and it says that the derivative of anything of the form x to the n equals n times x to the n minus 1. Now potentially this power could become negative, because if your n initially is smaller than 1, then you're going to get, a 0 power, and if it's a negative 1, it becomes negative 2, and so forth. So potentially these powers on x could become negative powers, and negative exponents mean that you're flipping it down and dividing by x's instead, so potentially you could be trying to divide by 0. So we just have to make sure in this note that to be differentiable at 0, in order for that derivative to exist at 0, x to the n minus 1 must be defined on an interval containing 0. So this is called your power rule, and you're just going to bring down the power and subtract 1 from the power. We're going to practice all of these rules once we get our little list together. Now the next two rules follow from the properties of limits that we've already talked about. We had a property of limits that said that the limit of a constant times a function is that constant times the limit of the function. Well, this is the same idea, but for derivatives. So the derivative of a constant times a function is that constant times the derivative of a function. In other words, if you have a coefficient in front of your function, then you can just leave that coefficient there and take the derivative of the function part and multiply the two together. We also had a limit property that said the limit of a sum or difference is the sum or difference of the limits. Same idea for derivatives. The derivative of a sum or difference is the sum or difference of the derivatives. You just take the derivative of each piece and then add or subtract the results. Now let's talk about the derivative of a trig function. So let's find the derivative of sine of x. And since we don't know what it is, we're going to have to fall back on our limit definition of the derivative to figure it out. So we need to find the limit of delta x going to 0 of f of x plus delta x minus f of x all over delta x. And in this function, our function is sine of x, so we want the sine of this input right here. So this first part, f of x plus delta x, becomes sine of x plus delta x, and you want parentheses around that whole quantity. And then we want to subtract from that just f of x, so that would become just sine of x. So here's what we have so far, and the only way to progress from here is to know a little bit about some identities. In fact, we need to know the identity for sine of a sum of two angles. And hopefully you remember this from pre-calculus or from trigonometry. And what this theorem says, or this identity says, is that you don't just distribute your sine across. That's not allowed. The sine of x plus delta x becomes sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. So sine of x plus delta x, and this is just based on that identity, is sine x cosine delta x plus cosine x sine delta x. And then we still have that minus sine of x on the side. So now we have all of this. What I'm going to do next is do a little bit of rearranging. This term here and this term here both have a sine of x involved. So what I'm going to do is group those two together, and I'm just going to do that by the commutative property. I'm going to switch these two terms around. So I'm going to leave the sine x cosine delta x where it is, and in the middle I'm going to put the minus sine of x, and then on the end I'm going to put the cosine x sine delta x. Next thing that I'm going to do is I'm going to factor out this sine of x that both of these terms have. So if I pull out my sine of x, then in parentheses I'll have cosine delta x left over from this first term, and I'll just have a minus 1 left over from the second term. And then over here I still have my cosine x and my sine delta x. And then the last thing I'm going to do is I have that division by delta x, and what I'm going to do is I'm going to break this sum up into two different fractions, and they're just going to have that delta x on the bottom of each, which I can do because I have a common denominator. So here's what I have so far. We have a limit of a sum is a sum of the limits. So if I can find the limit of this first fraction and then the limit of this second fraction, then I'm just going to add those two answers together. Now, to figure out these two limits, you have to recall something from, again, a previous lecture. We had some well-known limit properties or limit theorems of a couple of different special forms. This is one of those forms right here, and we derived this in a previous lecture. The limit as delta x goes to 0 of cosine delta x minus 1 all over delta x, that in the limit goes to 0. Also in that same lecture, we had that the limit as delta x goes to 0 of sine of delta x over delta x, that goes to 1. And that was that sine of stuff over stuff that we've seen before. So sine of x times something going to 0 is going to stay 0. And cosine of x times something going to 1 is going to stay cosine of x. So what we end up with is that this answer is just cosine of x. So this is something you want to memorize. The derivative of sine of x is just cosine of x. Okay? In a very similar proof, we can show that the derivative of cosine of x is minus sine of x. Remember that negative. It's a tricky thing to remember, but the derivative of cosine x is negative sine of x. Okay? We will derive the other trig functions eventually when we start talking about the product and quotient rule, so that will be in a different lecture. So for today, we just need to know the derivative of sine and the derivative of cosine. Now there's going to be one last rule that we're going to talk about before we start practicing, and that is the derivative of the exponential function e to the x. So again, to prove what this derivative is, we have to fall back on our limit definition of the derivative. So this time our function is e to the x. So if I want to know what f of x plus delta x is, this becomes my input, and that's going to go right up there in that power. So this becomes e to the x plus delta x. And then I want to subtract from that f of just x, so we're just going to use x up in that power, so this becomes e to the x. Now I'm going to use a property of exponents, which says that if you have the same base and you are multiplying two things with the same base, then you add exponents. So I'm kind of using that in reverse. E to the x plus delta x, if I break it down, is the same as e to the x times e to the delta x, because if you were to multiply these bases together, you would get to add those powers. So these are equivalent expressions. Now the reason I'm rewriting it that way is because now this term has an e to the x, and so does this one. So I can factor out that e to the x, and then in parentheses, I'll have e to the delta x minus 1, and I'm going to just put that delta x over that stuff in parentheses. And what we're going to do is we're going to try to figure out what this part of the limit goes to. And this actually comes from the definition of the number e. You all know that e is approximately 2.71828. It's an irrational number, and it's defined to be a limit. E is defined to be the limit as delta x goes to 0 of 1 plus delta x raised to the 1 over delta x. And in the limit, that goes to e. And you can check that numerically. I think we actually did this in a previous lecture. If you just use a table and you pick delta x's that get smaller and smaller, you'll see that this whole expression gets closer and closer to that number 2.71828. So this is a definition that we can take for granted. And what it means is that since this is a limit, this implies that for small m, for small delta x's, so when these delta x's get really close to 0, that means that 1 plus delta x to the 1 over delta x should be pretty close to e. So this limit being true means that for really small delta x's, this expression on the left side should be really close to what e actually is. Okay, so what I'm going to do is I'm going to just do a little bit of algebra on this semi-equation right here. What we're going to do next is we're going to raise both sides of this equation, if you will, to the delta x power. So what that does for us is, since this is a power to a power, you multiply these two guys together, and they multiply and cancel out to a 1. So the left-hand side just becomes 1 plus delta x. And that should be approximately the same as e to the delta x. Now if I subtract 1 from both sides, I get that delta x should be approximately e to the delta x minus 1. And so then if I divide by delta x, this left side goes to 1, and that means in the limit, e to the delta x minus 1 over delta x should be approximately 1. And if we take the limit of both sides here, then this little sort of approximate symbol right here becomes an equal sign. So in the actual limit of this right-hand side, that turns this into a straight equal sign, and that tells me that this, in the limit, goes to 1. So e to the x times 1 is going to stay e to the x. So what we've just proven is that the derivative of e to the x is e to the x right back again. And that's exactly why we use base e so much in higher level mathematics, because of this calculus rule right here. The derivative of the exponential function with a base of e is that same function right back again. Because that is such a nice clean formula, that's why we use base e instead of some other base. Okay, so the derivative of e to the x is e to the x right back again. So we have a bunch of rules now. Let's go ahead and put them into play. So let's start with a very basic example. Let's find the derivative of f of x equals to 2. So if we want the derivative of f of x, that's called f prime of x. And now, according to our rules, since this is a constant function, the derivative of a constant is 0. So f prime of x would just be 0. If we go to our next function, g of x is equal to 3x minus 1. And this is actually a difference of two different functions. So we're going to apply a couple of our rules. So to find g prime of x, I'm going to start by taking the derivative of this first piece, and then I'm going to subtract from that the derivative of the second piece. That's that rule that says the derivative of a difference is the difference of the derivatives. Now the derivative of this first piece is actually a constant times a power rule. So our constant multiplication rule says that if you have a coefficient in front, that coefficient 3 is going to stay put, and then we're just going to take the derivative of our x. And remember that x is like an x to the first, so if you bring that 1 down and then subtract 1 from the power, the new power on that x would be 0, and x to the 0 is just 1. So we get 3 times 1, or just 3. So the derivative of 3x is just that coefficient 3, because the x part goes to 1 when you take its derivative. Now we still need to subtract from that the derivative of 1, but that's a constant, so the derivative of a constant goes to 0, so that means my derivative function here is just going to be that 3. And we should have guessed that already, because g is a linear function with a slope of 3. So we know that the tangent line would be this same line itself, so the slope of the tangent line would be the same slope that this function has, which was 3. And a tangent line slope is a derivative, so we knew in advance that this answer should have been 3. Okay, let's go ahead and take a look at this next polynomial here. So we're just going to take the derivative of each individual rule, and some of these have coefficients, so that's going to be that constant multiplier rule. So f prime of x will be, if we start with this 2x cubed, the 2 stays put, and then the derivative of x cubed is a power rule. So you bring down the power, that 3 comes down, and then you subtract 1 from the power, so the new power will be a 2. And so when we simplify that, the 2 and the 3 end up getting multiplied together, so this is just going to be 6x squared. Now we go to our second term. The derivative of x squared, the 2 comes down, and then we subtract 1 from the power, so the new power will be 1. So the derivative of x squared is just a 2x. And then finally our 3x, the 3 stays there, and the derivative of x, we said, goes to just 1. So 3 times 1 will just be 3, so my final derivative is 6x squared minus 2x plus 3. Okay, the next one here is y equals 5x squared plus 2 sine x plus e to the x. So if I want the derivative of this, I need the derivative of y. Now just to review a couple of notations, you certainly could call this y prime, but it's also the same as dy over dx. That also means the derivative of y with respect to the variable that we're using here, which is x. So to start with, the derivative of 5x squared. The 5 will stay put, the 2 comes down, and we subtract 1 from the power, so it becomes an x to the first. So y prime is going to start off with a 10x. Then we go to our 2 sine x. That 2 is a coefficient, so it's going to stay there. And the derivative of sine of x, remember, is just cosine of x. So that middle term will just be 2 cosine x. And finally on the end, we have an e to the x. So the derivative of e to the x is e to the x right back again. So our derivative function overall is 10x plus 2 cosine x plus e to the x. Okay, and our next example here, same idea. So we want f prime of x, the derivative at any value of x. So the 3 will stay put because that's a constant, a coefficient. And then the derivative of cosine of x, remember, is minus sine of x. And what I usually do is I take that negative and I put it in front of my 3. So this would become negative 3 sine x. Now in order to do the derivative of square root of x, we didn't have a rule specifically that said how to take the derivative of a square root. So the only way to do this is to manipulate it and change it into one of the rules we do have. And we do have a power rule. So if we can change this square root x into an x raised to some power, then we would be able to apply that power rule. So this is something you should remember, that radicals are fractional powers, and the index of a square root is an implied 2, so that becomes the denominator of our fraction. So square root of x is really the same as x to the 1/2. So if I wanted to take the derivative of x to the 1/2, I would bring down the 1/2, and then we have to subtract 1 from this power. So be careful here. 1/2 minus 1 is 1/2 minus 2/2, or negative 1/2. So the new power on the x turns out to be a negative power, a negative 1/2. If you wanted to rewrite that, which I would probably recommend, you could take that negative exponent, and negative exponents flip you down into the denominator. So this x to the 1/2 would now be in the denominator, and we could take this 2 that was in the bottom of our 1/2 and stick it in front, and the only thing we would have left on top now is a 1. One step further would be to take that x to the 1/2 and turn it back into a square root. So we could rewrite this as negative 1 over 2 square root of x. These are all options, but especially if you're going to do something with your derivative, like plug in a number or set it equal to something, I would recommend that you try and simplify as much as possible. Now to finish this problem off, we just have to take the derivative of our last term over here, our e to the x, and we know that the derivative of e to the x is e to the x right back again. So our final derivative turns out to be minus 3 sine x minus 1 over 2 square root of x minus e to the x. Now the next few examples that we're going to do are kind of similar to the last one, in that when you first look at them, our derivative rules that we know so far do not apply, because we haven't talked about how to take the derivative of a quotient, how to take the derivative of something divided by something else. Unfortunately, it doesn't work that you can just take the derivative of the top and the derivative of the bottom and divide those two answers. That is not allowed. It's actually a much more complicated quotient rule, which we will save for another day. So if you were presented with the function 2 over 3x squared, the only way we're going to be able to take a derivative of this using the rules we know so far is to manipulate this and try to turn it into some kind of power rule. So the first thing I'm going to do is I'm going to take this coefficient out front, this 2/3, and I'm going to push it out front. And then I'm going to notice that if I have an x squared in the bottom, I don't really want x's in the bottom because I don't know how to take the derivative of an x down in the denominator. What I want to do is I want that x to be on the top raised to some power. And we can do that because if you flip it up to the top, it becomes a negative exponent. So 2 over 3x squared is exactly the same thing as 2/3 x to the negative 2. But when I put it in this new form, now it becomes a constant multiplier times a power rule. And we have both of those rules available to us. So f prime of x will be the constant multiplier stays put, and then the derivative of x to a power is to bring that power down, so bring down the negative 2, and then we subtract 1 from the power. So when I subtract 1, negative 2 minus 1 gives me a negative 3. Now I would, again, strongly recommend that you clean this up a little bit. So 2/3 times negative 2 would be negative 4/3, and then I'm going to take that x to the negative 3 and move it back down to the denominator by making the power positive. So my derivative function is negative 4 over 3x cubed. Okay, so the next one is pretty similar to that. Not only do we have a fraction, which we don't know how to deal with, we also have some parentheses, which we don't know how to deal with. So we will learn rules for figuring out how to do this, but the easiest way to handle this is just to rewrite this in a different way so that it becomes like a power rule. So the first thing I would recommend is go ahead and square that denominator to get rid of your parentheses. So this becomes 49x squared. And then this is very similar to the last example. We can simplify this by taking that coefficient, that pi over 49, and putting it out front. And then we can take that x squared, which is in the bottom, and move it up to the top by making the power negative. So then y prime would be that coefficient stays put, and then the power gets brought down, and when we subtract 1 from the power, the new power is a negative 3. And rewriting this a little bit nicer, pi over 49 times negative 2 becomes negative 2 pi over 49, and that x cubed can move back down to your denominator. So here's our derivative. Okay, the next one here is another one of these big fractions. So again, you're not allowed to take the derivative of the top and then the derivative of the bottom and just divide those two answers. That is not the correct answer here. So I'm actually going to show you two different options. You can use whichever method you prefer. So the first option is kind of similar to the last two. What I'm going to do is I'm going to take that numerator and I'm going to wrap it in parentheses momentarily. And what I'm going to do is I'm going to take this x and I'm going to move it up to that level, up to that top level, by making the exponent negative. And since there's multiplication between that x to the negative 1 and this stuff in parentheses, we can distribute that x across. And remember that when you multiply these x's that have the same base, you're adding the powers. So 2x squared times x to the negative 1 becomes 2x to the positive 1, since 2 plus negative 1 is 1. Then when I go to my middle term, I have a minus 3x times x to the negative 1. This x has a power of 1. 1 minus 1 would be 0, and x to the 0 is just a 1. So the x's actually cancel each other out, so we're just left with that 3. And then on the end here, 1 times x to the negative 1 is going to stay x to the negative 1. Now this is still our y. I haven't done a derivative yet at all. The only thing I've done is manipulate this function to try to turn it into a bunch of power rules instead of a big fraction. So this is still y, but now I'm ready to do my y prime. So the derivative of 2x, the 2 stays put, and remember the derivative of x goes to 1. The derivative of minus 3 goes to 0. And the derivative of x to the minus 1 is a power rule, so we bring down that minus 1, and when we subtract 1 from the power, this becomes a minus 2. So rewriting this just a little bit nicer, we get 2 minus 1 over x squared. So there's my derivative. Now that's option number 1. Option number 2, instead of bringing that x up and distributing it across, instead what I could do is I could break up this great big fraction. Since what I'm dividing by is a monomial, a single term, I could break it up into 3 separate fractions. So 2x squared over x minus 3x over x plus 1 over x, and then simplify each of these. So 2x squared over x becomes 2x. In the middle, the x's cancel, giving me just that minus 3. And the last one doesn't reduce, but I don't like having that x in the bottom, so if I move that x to the top, I get that x to the negative 1. And that is exactly what we had before when we distributed that x to the negative 1 across. So this is the same as this. So that means the derivative will be the same as what we got over here. Derivative of 2x is 2. The derivative of the minus 3 goes to 0, and the derivative of x to the minus 1 is minus x to the negative 2. And if you flip it back down, you get the same answer no matter which way you decide to do it. So bring the x up and distribute, or break this up into 3 fractions and reduce each one. Okay, the next example has some radicals in it again, so I want to review with you how to rewrite these correctly using powers. So cube root of x, that index right there is a 3. So to rewrite that x as a power, you have to know that that index becomes the denominator of your power, so cube root of x is just x to the 1/3. So on the next one over here, now the index is a 5, so the fractional power will have to have a 5 in the denominator, but this one also has a power inside of your radical, that 3, and that becomes your numerator. So the only way to take the derivative of this is to rewrite these radicals as fractional exponents, so that now they become power rules. So I haven't done my derivative yet, I just rewrote my function, and now to take the derivative, y prime, we're just going to bring the power down, and then we need to subtract 1 from the power. So 1/3 minus 1 is 1/3 minus 3/3, or negative 2/3. Then when I go to the next piece over here, x to the 3/5, I bring down that power, 3/5, and then I need to subtract 1 from the power. So 3/5 minus 1 would be 3/5 minus 5/5, or negative 2/5. Now you could stop here. If it was just the question of take a derivative and then you're done, then I would stop here. But if you need to do something with this derivative, then I would strongly recommend that you rewrite this back in terms of radicals. So let me show you how to do that. So here's one correct answer. But if I rewrite it, I'm going to take this 1/3, and I'm going to put a 1 on top and a 3 on the bottom, and then I'm going to move this x to the 2/3 back down to a positive. Now if I change that into its radical notation, because the 3 is your denominator, that means this is a cube root, and because the 2 is your power, I'm going to put that 2 on the inside and make this an x squared. So 1/3 x to the negative 2/3 is really the same as 1/3 cube root of x squared. Now let's do it for the second fraction. We have 3/5, and I'm going to move that x to the negative 2/5 down to the bottom so it becomes positive. And then the 5 is in the denominator, so this needs to be a 5th root, and the 2 is in the top, so I'm going to have an x squared underneath that 5th root. So this would be my answer back in terms of radicals. Okay, so far all we've done is take a derivative and then stop. So now what we're going to do in this next example is find the derivative, but we're going to find it at a specific point, 3/5, 2. So we still need to take a derivative, but then we have an actual x value, which is going to be this 3/5, to plug in once we've found that derivative. So let's start by trying to take a derivative of this. And I can't do it right away because of this 3/5x. I don't have a derivative rule to deal with this kind of a quotient or this kind of a fraction. So the first thing I'm going to want to do is rewrite this function. I'm going to leave the 3 the way it is, and then I'm going to take this coefficient 3/5, put it out front, and then I'm going to move that x up to the top and make this an x to the negative 1. So now I have a constant multiplier times a power rule. So the derivative of this would be, well, the derivative of 3, that's a constant, so that goes to 0. Then I have my minus 3/5, that's going to stay there, and my power rule says to bring down the minus 1, and then when I subtract 1 from that power, the new power is going to become a minus 2. Let's clean this up. So I get a negative times a negative is a positive, and then I'm going to take that x to the negative 2 and move it back down to the denominator next to that 5. So my cleaned up derivative will be 3/5x squared. So now all I have to do is use this point, and this derivative formula is only involving x, so I only really need the x coordinate. And we're just going to take this derivative and figure out what it is when x is 3/5. So let's plug in 3/5 for this x. So let's square our denominator. 3/5 squared becomes 9/25. 5 cancels out one of the 5's in the 25, so this becomes 3/9/5. 3 divided by a fraction is the same as 3 times the reciprocal of that fraction. 3 goes into 9 3 times, so what I have left is a 1 times 5, or 5, over that 3. So my derivative at this point is 5/3. Okay, next example, pretty similar, but we're going to take it one step further. This time we want to find the equation of the tangent line to this function at a point, but we don't just want the derivative at that point, we want the actual equation of the tangent line. So we're going to need to use that point slope form, y minus y1 equals m times x minus x1 to get our equation of our line. We already know the x1 and the y1, that's this point right here. What we don't know yet is the m, and that's exactly what our derivative is. A derivative is the slope of our tangent line. So how do we find our derivative? We have to look at our function. And unfortunately, this one has parentheses in it, and I haven't told you any rules for how to take the derivative of something involving parentheses. So the only way to take this derivative is to manipulate this function first and turn it into something we do know how to take a derivative of. So the best or easiest way to manipulate this is to go ahead and square out this quantity to get rid of those parentheses. So 5 minus x quantity squared will be a 25 minus a 10x plus an x squared. Don't forget your middle term. And then we still need to distribute that 3 across. So my function is 75 minus 30x plus 3x squared. Now I haven't done a derivative yet. All I did was rewrite this function in a different way. And now it's just a polynomial. So to take the derivative of this polynomial, we just go term by term. Derivative of 75 goes to 0 because it's a constant. The derivative of minus 30x, the minus 30 will stay there. The derivative of x is just a 1, so that goes away. And then the derivative of 3x squared, the 3 is going to stay there, but I'm going to bring down that 2 next to it. So 3 times 2 will give me a 6. And when I subtract 1 from the power, this just becomes an x to the first. So my derivative function is negative 30 plus 6x. This tells me the derivative or the slope at any x. What x do we want to know the derivative at? We want to know it when x is 5. So let's find f prime of 5. So if I plug in 5 for x, I get negative 30 plus 30, so I get 0 for my derivative. And remember, this derivative is the m that we're going to use in our equation of our tangent line. So this is the slope of our tangent line. So now we know the m. We already knew the x1 and the y1, so we're ready to plug everything in. So the equation of the tangent line becomes y minus the y value of our point, which was this 0, equals our slope, which we just found was also 0, times x minus our x value of our point, which we knew was 5. Well, 0 times anything is 0, so this whole right side is 0, and y minus 0 is y. So here is the equation of our tangent line. Notice what kind of a line it is. It's y equals a constant, which means it is a horizontal tangent line. And that was also true because it had a slope of 0, and lines with a slope of 0 are always horizontal. Okay? Alright, let's try this process again, but this time we have a different function. We want to find the equation of the tangent line to the function f of t equals 2 plus 3 cosine t at the point pi comma negative 1. So your starting point is always to find the slope of this tangent line, that m, and m is just the derivative evaluated at this point. So let's find the derivative function first, f prime of t. The derivative of 2 goes to 0, the 3 will stay put, and the derivative of cosine is minus sine t. So f prime of t is negative 3 sine t. So what's the derivative at the point in question? Well, the x value of this point is that pi. So I'm going to plug in pi. So what is negative 3 times the sine of pi? Well, what's sine of pi? Sine of pi, that's 180 degrees on your unit circle, and the y-coordinate at 180 degrees is 0, and the y-coordinate is your sine. So this is 0, which means we have another 0 slope. So we're going to end up with another horizontal line. So this 0 that we just figured out, that is our m. So now to get the equation of our tangent line, we're going to do y minus this y value, so you do get a double negative there, equals our slope, which we just figured out was 0, times x minus our x value, which was pi. Again, because the slope is 0, this all goes to 0. The left side becomes a y plus 1, so when I subtract that 1 over, the equation of my tangent line is -1. Y equals -1. Another horizontal tangent line. Now, horizontal tangent lines are quite important in calculus because if you remember when we were talking in a previous lecture about how to sketch the graph of a derivative, we did that by starting by looking for those maximums and minimums because they had those flat horizontal tangent lines with a slope of 0. So knowing where you have horizontal tangent lines is a very common question. So let's explore that a little bit more. So let's start with the function x cubed plus x. If we want to know where the tangent line is horizontal, you have to first understand that if a line is supposed to be horizontal, then it has 0 slope. And slope of a tangent line is the same thing as a derivative. So we need to know where is this derivative going to be 0, because that's going to be where the slope is 0. So whenever the question says, find where you have a horizontal tangent line, all you have to do is take your derivative, set it to 0, and find out for what values of x's that happens. So let's start with this function. If we want to know where the slope is 0, we need to find where the derivative is 0, since that's what slope is. So let's find our derivative function. Derivative of x cubed is 3x squared. Derivative of x just goes to 1. So where is this going to be 0? Well, we just force it to be 0 and we solve. So let's solve this. You might be able to just see it right away, but if I subtract 1 and divide by 3, this is trying to give me an x that when I square it, which you always know is going to be positive, is supposed to equal a -1/3. So when is that going to have a solution? It won't. It doesn't have a real solution, and in calculus we're only going to be dealing with real numbers. So there are no real x's where this is true, because you would be trying to take the square root of a negative number. So this has no solutions, which means there are no values of x where the tangent line is horizontal. So this means we have no horizontal tangent lines. So if you were to graph this function, you wouldn't see any of those little maximums or minimums anywhere because there aren't any horizontal tangent lines on the entire graph. Okay, let's try it again. This time my function g of x is square root of 3 times x plus 2 cosine x. Notice the x is not under the radical. So if we start by taking our derivative, which you need to know because that's your slope, and we're trying to find where the slope is 0 since we want it to be a horizontal line, and horizontal lines have 0 slope, then this derivative would be the square root of 3. That's just a constant, a coefficient out front, so it's going to stay there, and the derivative of the x goes to 1. So the derivative of square root of 3 times x is just square root of 3. And then we go to the 2 cosine x part. The 2 will stay there, and the derivative of cosine is a minus sine x. So I'm just going to put that minus out front and make it a subtraction. So here's our derivative function. So this is our slope everywhere, and we want to know when is this slope going to be 0. So we're going to actually set it equal to 0 and force it to happen and solve for x to find out when this happens. So to solve this, what I might do is add that 2 sine x over to the other side, trying to isolate that x, and then divide by 2. And then again, you have to know your unit circle. It's expected that you have those common angles memorized. So where on our unit circle does the sine value, which is the y coordinate, give you root 3 over 2's? And hopefully you remember that those are those pi over 3 angles. Pi over 3, sine of pi over 3 is square root of 3 over 2. And we want to know where it's positive root 3 over 2. So that is going to be the pi over 3 angle in quadrant 1, and the other quadrant where the y coordinate is positive is quadrant 2. So this guy is called pi over 3, and this one in quadrant 2 is called 2 pi over 3. The other two down here would not work because they would be negative root 3 over 2 because they're in quadrants 3 and 4. So only pi over 3 and 2 pi over 3 work when we're in one revolution from 0 to 2 pi. So at these 2 points, at x equals pi over 3 and 2 pi over 3, we have horizontal tangent lines. So if you were to sketch the graph of this curve, you would see either maximums or minimums at those two x values. Okay, the next example is pretty similar to some of the other ones we've just been talking about, but there's one important difference, and this difference makes the problem a lot harder. So this one's going to be a tricky one. We want to find the equation of a tangent line to the function 2 over x through the point 5, 0. Now this sounds pretty similar to the problem we did up here, number 11. Find the equation of a tangent line to this function at 5, 0. The difference is that that 5, 0 in the last example we had was on the actual curve, and it was the point at which we were tangent. 5, 0 is not on this graph. So let me draw you a picture so you can see what we're talking about here. Now the function 2 over x is a reciprocal function. So it has a graph that looks like this. 2 different branches. It's asymptotic to the y-axis, so it never crosses, and it's asymptotic to the x-axis, so it never crosses. So 5, 0 is over here on the x-axis. So obviously this graph cannot cross because it never hits the x-axis. Notice that that point, 5, 0, is not the point on the curve where our tangent line goes through. But there is exactly one tangent line that is tangent to this curve and also goes through 5, 0. And let's see if we can draw in what that tangent line might have to look like. It's got to hit our curve exactly once and also continue through and hit 5, 0. Now this point where it's hitting our curve, that would be our point of tangency. And we're not told at what point that is. So the difference between this problem and the last one is that the earlier problem, we knew what this x value was right here, and then we could just take our derivative and plug in that x. In this problem, we don't know what that x value is. It's just some random point x, y. So I don't have an x that I can just plug in to find the slope of my tangent line. So how are we going to find the equation of this tangent line? Well, we know that to find the equation of any line, you need y minus y1 equals m times x minus x1. We know a point because 5, 0 is on this line. So we know an x1 and a y1. What we don't know is that m. So how can we come up with this slope of the tangent line? Well, we're going to do it in 2 different ways. So option number 1 is to find the slope of the tangent line using calculus. What do we know about the slope of a tangent line? It's the same thing as a derivative. That's what the derivative is defined to be, the slope of the tangent line. So the slope of the tangent line could be calculated by finding the derivative f prime of x. So we can do that. We know how to do that. How do you find the derivative of this function 2 over x? Well, before I do that, I better rewrite it by moving that x up to the top and thinking of this as 2x to the negative 1. So if that's my function, then the derivative of it, f prime of x, would be the 2 stays put and gets multiplied by that negative 1 that gets brought down. So this is going to turn into a negative 2. And then when we subtract 1 from the power, then this new power will become a minus 2. And since we're going to be doing some stuff with this, let's go ahead and clean that up a little bit and just move that x squared back down to the bottom. So we just found our general derivative at any point x. Unfortunately, we don't know what x right here to plug in. Otherwise, I would have my m right away. So here's what we're going to have to do. We're going to have to see if we can find this slope of the tangent line in a second way. So think about how we could find the slope of this line right here doing some other method that doesn't even involve calculus. Well, we know from basic algebra that the slope of a line is just the change in the y's over the change in the x's. And I have 2 points on this line, so I can subtract the 2 y's and subtract the 2 x's, and that should calculate for me the slope of this blue line. So let's find the slope of this line by doing change in y over change in x. So this slope m would have to be this y minus this y, 0, over this x minus this x, which was 5. So simplified, this becomes y over x minus 5. Now that's okay, but it's not great because it involves a couple of different variables. It involves both the x and the y. So is there something else we know about the relationship between x and y? Sure, we know that since this point right here, that point of tangency, is on this function right here, there is a relationship between that x and y that's just determined by this formula right here. According to this formula, f of x, otherwise known as y, is always equal to 2 over x. So this y coordinate right here would have to be 2 over whatever x is. So I'm going to use that relationship between x and y to reduce the number of variables. I'm going to swap out this y right here with 2 over x, and now I have a new slope formula that only involves x's. It's still messy, but it's still doable. So my slope, by doing change in y over change in x, is 2 over x divided by x minus 5. So what we've done so far is we've found the slope by looking at a derivative, and we've found the slope by looking at change in y over change in x. Well, what do we know about these two slopes? Well, since we're talking about the same line, they should be the same, right? This slope here should equal this slope here. So let's set them equal to each other and solve for when those two slopes will be equal. So this is a way of getting an equation that we can actually solve to find out what x needs to be. Now, it's kind of a yucky equation because it's got a complex fraction in it, but it's essentially just a proportion. You have a fraction on the left and a fraction on the right. So a very quick, easy way to simplify this is just to solve the proportion by cross-multiplying. So I'm going to multiply this direction and get negative 2 times that quantity x minus 5, and that diagonal has to equal this diagonal here. So x squared times that 2 over x. Now let's go ahead and simplify. On the left side we get negative 2x plus a 10, and on the right side one of these x's is going to cancel, giving me just a 2x. So if I add my 2x over, this is just a linear equation, so I can solve for x now by dividing by 4, and 10/4 reduces to 5/2. So we now know what this point is right here. X is 5/2. Now, how could we find out what the y is? Use your function. Remember, there's a relationship between this x and that y. If you know what x is, then you know what y is. Y would have to be 2 over that x of 5/2, which is 2 times the reciprocal, 2/5, so this would be 4/5. So that's my point of tangency right there. Now I know at what point I go through. Have we answered our question? Not quite, because what we were looking for was the equation of the tangent line. So we need to know a point, and I actually know a couple points now. I know this point, and I know this one, and I also need to know my slope m. Have I figured out what my slope m is yet? Not quite. We found formulas for what the slope is, but now that we know what x actually is, we now have an x that we can plug in to either one of these two formulas to find out what the slope is right at that point of tangency. So to find the m, we're going to need to plug in 5/2 for x, either into here or into here. Personally, I like this one, the derivative, better because it seems a little bit simpler. So to find m, we're going to take this function -2 over x squared, and we're going to let x be that 5/2, that point of tangency. So the slope will be -2 over 5/2 squared, which becomes -2 over 25/4, which becomes -2 times 4 over 25. So my slope is -8 over 25. So we know our m, -8/25, and we know a point. You could use either one of these 2 points because they both lie on that blue line. Personally, I like the 5, 0 because the numbers are simpler. So now that I know my point and my slope, we can use our point-slope form to get our equation. So finally, our tangent line is y minus this y value 0 equals the slope times x minus this x value 5. Y minus 0 is y, and if I distribute, I get -8/25 times x, minus times minus is plus, and this 5 will cancel with the 25 and reduce to 8/5. So my tangent line is y equals -8/25 x plus 8/5. So the reason why this problem was so difficult was because we weren't given the point of tangency. We were just given this other point that lied on my tangent line. So I didn't have an actual x that I could plug into my derivative right away. So what we had to do was find the derivative, and then we also found the slope using change in y over change in x and substituting in my formula for my function. And then I equated these 2 slopes and solved for x to find out when that would happen. And that's how we got that 5/2. And once we found our 5/2, then we could plug in 5/2 into our derivative to find the slope m, and then do our point-slope form. Okay, so that's a tricky problem. Okay, what we're going to move into next is how derivatives relate to rates of change. So first, let's talk about an average rate of change for a function t squared minus 3 on the interval 2 to 2.1. Now this is kind of a review from when we were first talking about tangent lines and secant lines and things like that. What we talked about in the past is that the average rate of change turns out to be the slope of the secant line, and it's going to always be given to you over a certain interval of time. You always have to have a starting time and a finishing time, an A and a B, for example, or a time 1 and a time 2. And the average rate of change would be the change in the y's over the change in the x's. So for this particular problem on this particular interval, that would look something like this. The y value at the later time, 2.1, minus the y value at the earlier time 2. There's your change in your y's. And on the bottom would be the difference in these 2 times. So 2.1 minus 2. So average rate of change is just your typical slope of your secant line, because these are 2 points on the line. We're not just going through 1 point, we're going through 2 points. Now to actually compute this, you would just take 2.1 and plug it into your function. So 2.1 squared minus 3 turns out to be 1.41. If I plug in 2 into my function, 2 squared is 4, 4 minus 3 is 1. And on the bottom we have that 2.1 minus 2. So subtracting, I get 0.41 on the top, 0.1 on the bottom, and when I divide, this becomes 4.1. So your average rate of change always has to have an interval given to you. You have to have a time 1 and a time 2, and it represents physically on a graph the slope of the secant line between your 2 endpoints, your two times. So in this case, that would be between 2 and 2.1. Okay, so if we were to draw a graph of this parabola, it's a parabola that's been shifted down 3 units, then we would have something like here's 2 and maybe here's 2.1. The line between those two, the slope of that line is exactly what we just calculated, this average rate of change. Now let's contrast that with the instantaneous rate of change. You don't see that word average anymore, you see the word instantaneous. And an instantaneous rate of change will not give you 2 different times, it will just give you 1. So comparing that to our graph up here, this time we just want to know the instantaneous rate of change right at 2. And that is exactly your tangent line. So for instantaneous, you're talking tangent lines. For average rates of change, you're talking secant lines. And what is the slope of a tangent line? That is a derivative. So in this problem, we would be looking for this derivative specifically when t is 2. Okay? So we have to start by finding the derivative of our function in general, and fortunately it fits all of our nice rules that we've just learned today, so we can use some shortcuts. Derivative of t squared, you bring down the 2, subtract 1 from the power, and the derivative of 3 goes to 0 because it's a constant. So that's your derivative anywhere. What's your derivative right at 2? Well, if I plug in 2 for t, then this is going to give me 4. So the slope of this tangent line is equal to 4. And this instantaneous rate of change will be the slope of the tangent line. Now just to refresh your memory really quickly, the closer this time interval gets to 2, in other words, the closer these two endpoints are to each other, and the smaller this little width becomes, the closer the average rate of change gets to the instantaneous rate of change. So if I made these 2 points closer together, then I would get an even better approximation to that 4, to that instantaneous rate of change. So whenever you see the word instantaneous in calculus, that means a derivative. Now a common use for rates of change are going to be in physics when we're talking about describing the motion of an object moving in a straight line. And just to kind of get some conventions down, in calculus, whenever the object is moving up or to the right, that is considered the positive direction. And whenever your object is moving down or to the left, that's considered the negative direction. In physics and sciences, usually instead of using f of x notation to talk about the position of an object, you'll actually see s of t. S represents the position or the displacement of the object, and t is time. So you'll typically see this in that notation, s of t. So the average rate of change in physics would represent the average velocity if we're talking about a position function over time. And the formula that you want to have memorized here is that average velocity is change in position, change in s, over change in time. So if you were given a time interval, which you would need to be given in order to find an average rate of change, then this would just be the position at time 2 minus the position at time 1 over time 2 minus time 1. You want to memorize that. That is our formula for average velocity. Change in position over change in time. And just as a little side note, you could do s of t1 minus s of t2 over t1 minus t2. That would work as well. You just want to be consistent on the top and the bottom. So average velocity gives you this interval of time, and you're just finding the change in position over the change in time. Now instantaneous rate of change would be called instantaneous velocity when you're talking about position functions, and that is a derivative. So the notation that you'll see is s prime of t, and sometimes we call that the velocity function, v of t. You may or may not see this word instantaneous. Sometimes they might just say velocity. What is the velocity? And if you see that, then that is implying the derivative. If they meant average velocity, then you would have to see the word average in there. Okay? Now, something else from physics that we're not going to derive, but something that you will see and you'll want to be able to utilize is this known position function. The position of a free-falling object, neglecting air resistance, under the influence of gravity can be represented by this equation. The position of the object at any time t equals 1/2 gt squared plus v sub 0 t plus s sub 0. S sub 0 is the initial height of your object, v sub 0 is your initial velocity of your object, and g would be acceleration due to gravity. You've probably heard of g forces before. That's that same g. Now, depending on what units you're using, on Earth, the value of g is negative 32 feet per second squared if you're using those units, or negative 9.8 meters per second squared if you're using international units. So again, the s sub 0 would be your initial height. So if you were starting at the top of a building, for example, that would be your s sub 0. And then if you threw the ball up into the air, it would fly for a while, but then eventually gravity would pull it back down. The force or the speed at which you threw that ball would be your initial velocity. If I'm throwing it upwards, then that initial velocity would be positive. If I was throwing the ball down, then that initial velocity would be negative. So let's try a couple of examples with this. Let s of t equal negative 16t squared plus 32t plus 48. And this represents the height of an object propelled from a cliff 48 feet high. So the first question is to find the average velocity over the following time intervals. So this is just that basic formula, change in s over change in t, change in position over change in time. And these are my two different times that I'm looking at. So the velocity, the average velocity would be position at time 2 minus position at time 1 over 2 minus 1. So let's go ahead and find out what those are. To find position at time 2, you're just plugging in 2 into this formula. So negative 16 times 2 squared plus 32 times 2 plus 48. And that turns out to equal 48 feet. To find the position at time 1, we would just plug in 1. So negative 16 plus 32 plus 48, that's 64. So what we end up with here is 48 minus 64, which is negative 16, divided by 1. So this average velocity will be negative 16. What kind of units would be on this? Well, since it's an average velocity, which is a position over a time, these positions are measured in feet, and these times are measured in seconds. So this would be negative 16 feet per second. And the fact that it's negative means that this velocity is going in the downwards direction. This object is on its way down. Okay, so let's try that again, but this time we're going to do it on a smaller interval, closer to 2. So we're going to find the average velocity from 2 to 2.1. So this average velocity would be the position at time 2.1 minus the position at time 2 over 2.1 minus 2. So if we take 2.1 and plug it in for these two t's, I'm going to leave that to you to do on your calculator, it turns out to give you 44.64. And if you were to plug in 2, we knew that that was 48. So when I simplify, you're going to get that this reduces to negative 33.6, and again the units would be feet per second. So now my average velocity is actually a little bit larger, negative 33.6 feet per second. Okay, so average velocity is just change in positions over change in times. Now let's find the instantaneous velocity when t equals 2 seconds. And they may not say that word instantaneous. If they just said find the velocity when t is 2, that implies instantaneous, which implies use a derivative. So this is really asking for s prime of 2. And in order to know that, we need to know s prime of t first. Because we have these new shortcut rules for taking derivatives of a polynomial like this, let's go ahead and use them. So derivative of negative 16 t squared. When I bring down that 2 and multiply it by the negative 16, we're going to get a negative 32. And the power on the t goes down by 1, so it goes to just a t. Then the derivative of 32t, the 32 stays put, and the derivative of t goes to 1, and the derivative of the 48 goes to 0 because it's a constant. So here's my velocity function. You could call this v of t. This is your velocity at any time. We want the velocity at time 2. So I'm just going to plug in 2 seconds for t. So that's going to give me negative 64 plus 32, which is negative 32. And again, the units would be the same as they were for average velocity, feet per second. So this is my velocity at time 2 seconds. Notice that on this interval that was fairly small and close to 2, the average velocity is fairly close to the instantaneous velocity. And the closer I make these two times to 2, the closer the average and the instantaneous velocity will be. Okay, the next question, still using this same position function. When is the time, or find the time when the object reaches its maximum height. So let's visualize what's going on here. We have this object, it was starting 48 feet off the ground, off this cliff, and we're propelling the object up into the air, and then gravity pulls it back down. So we're trying to find when this object reaches its maximum height, which you can clearly see from my picture would be right about here. So we want to know the time it takes for it to reach that peak. Now you can do this lots of different ways. You can do this using algebra, or you can do this using calculus. We're obviously going to use some calculus here. So notice something that's true about this maximum height. What would the little tiny tangent line look like right at that peak? If you were to sketch it in, it would be horizontal, which means right at that maximum, the slope, otherwise known as the derivative, is going to be 0, because this is a horizontal tangent line, and horizontal tangent lines have a slope of 0. So all we need to do to find this maximum height is to find where the derivative equals to 0. And what is the derivative of this? Well, we already calculated that in the last example. The derivative of this position is actually velocity. And we already found out what the formula for that velocity or that derivative was. It was negative 32t plus 32. So all I have to do to find out when this is 0 is set it to 0 and solve for t. So if we subtract that 32 over and divide by negative 32, then we get that when the time is 1, and the units here would be seconds, when the time is 1 second, this little object is at its peak. Okay? So there's our answer. It reaches its maximum height at time 1 second. All right, the next part of the question is, okay, you know when it's reaching its maximum height, but what is the maximum height? So let's find the maximum height obtained by the object. So we want to know how tall this actually is. Now, is that a velocity? Is that a time? Or is that a position? It's a position, right? It's a height. So to figure out this height, we need to go back to our height function, which is also known as position, s of t. So here we need to go back to our original function, negative 16t squared plus 32t plus 48. And if we want to know the height, which is this side, then we need to know a time to plug in. And we know that from the previous question, we know that we reach this maximum at 1 second. So this question is really just asking for s of 1, the position of this object at 1 second. So all I have to do is plug in 1 into the original function. So that's going to give me negative 16 plus 32 plus 48. So that's 16 plus 48, or 64. And remember, this is a position or a height, so the units would be feet. This reaches a maximum height of 64 feet before it comes back down again. Okay? Okay, let's try one more example like this. This time we have that at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position of the diver is given by s of t equals negative 16t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. So to help you visualize this, we have this diving board, and it's 32 feet above the water level, and our diver jumps up and then eventually splashes down into the water over here. Okay? So notice that we are measuring from the water level because you see that plus 32 on the end of our function. So height 0 is right here at the water level. So this is going to be your position of 0, height 0. So that's going to help us when we answer this first question. When does the diver hit the water? Well, we know that when the diver hits the water, he's splashing right here at a height of 0. So if this is our function right here, we want its height to be 0. So all we have to do is plug in 0 in for that position, that s of t, and we have to solve this for t. So this is actually just an algebra question. Doesn't involve any calculus. You just have to realize that hitting the water corresponds to occurring at a height of 0. So plugging in 0 for that s of t. Now how do we solve this? Well, it's quadratic, so you really have your choice of method here. You can do it any way you like. I'm going to try factoring. All of these constants here are divisible by 16, and I don't personally like leading off with a negative, so I'm going to factor out a negative 16. And when I do that, that's going to change these two signs over here. So when I pull out my negative 16, I'll have a t squared left, a minus t, and a minus 2. So when I finish factoring, use reverse FOIL on this trinomial. I need a t and a t, a 2 and a 1, a minus for the 2, and a 1 to be positive so that I get a negative middle term. So this factor gives me negative 1 for t. This factor gives me 2, and this coefficient out front here doesn't have a variable, so it doesn't contribute any solutions. There's no t next to that 16. So my only two solutions are 2 and negative 1, but remember this means time. T is time, and you can't have a negative time. So what this means is that the diver hits the water after 2 seconds. Okay? So now, part B, what is the diver's velocity at impact? So how fast is he or she going into the water right as they splash in? So this doesn't say instantaneous velocity, but it's implied. So when it says velocity, it means that v of t, which means the derivative s prime of t. So to find this velocity, we need to take the derivative of this position function. And this is a nice polynomial, so we can just use our shortcut rules. The derivative of negative 16t squared, I would bring down the 2, so negative 16 times 2 would be negative 32, and subtract 1 from the power, so the new power on t would just be t. And then the derivative of 16t, the 16 stays put, the t goes to 1, and then the derivative of 32 goes to 0. So here's my velocity function. At impact, that occurs at time 2 seconds. We just figured that out. So the velocity at time 2, we just plug in 2 for this t, and we would get negative 64 plus 16, which is a negative 48. And this is a velocity, so my units would be feet per second. Notice that this is negative because the diver is splashing down into the water, so that negative direction is showing up in the fact that we have that negative. Okay? All right, the next two examples are going to ask us to find some derivatives from a graph. So I'm not giving you a position function, I'm giving you a position graph and asking you in question 18 here to sketch the graph of the velocity function. So this represents the position of some object over time. We want the graph of the velocity function, and the velocity is the derivative. So over here, when I graph my v of t, you have to keep in the back of your mind that velocity is the derivative of position. So how do you get the graph of a derivative? That is by sketching in those little tiny tangent lines, and then the y values that you plot over here correspond to the slopes of the tangent lines from over here. So let's start by looking for some of those nice, flat, horizontal tangent lines. We have a little maximum right here at about 2. So the slope of this line right at 2 should be 0 since it's horizontal, which means the y value that I plot over here at 2 should also be 0. The y values that we plot here correspond to the slopes from over here. So since this slope is 0 at 2, we need to plot a 0 at 2. Notice over here that all of these little tangent lines in this little constant stretch of the graph are all 0 slopes as well, because they're all horizontal. So for every x value from 3 on, the slopes should be 0. So for every y value over here from 3 on, that y should be 0. So all of these y's are 0 going in this direction. Now let's look at what happens on either side of 2. So let me move this guy out of the way. We know that this little tangent line right here, notice that it's rising up slightly, so that's a positive slope. And then it's a little bit steeper as we move to the left. These get a little bit more vertical as I move to the left. So they're still positive. These are all positive slopes, but they're getting larger positive. So as I go to the left, I want positive y values that are getting larger, more and more positive. So you'd get something like that. Now if I go to the other side, let me use a different color. Here, this little tangent line falls, so it's a negative slope, and then it's a little more steep, a little more vertical, a little more vertical. So these are going to continue to be negative slopes, but they're getting more and more negative. So these points would be going down, 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 down until we get to that 3. So if we continue this trend, this would be my graph so far. Now the last thing we need to think about is what happens right at 3. We call this point right here a kink, and what that means, and you should remember this from a previous lecture, is that there is no derivative at a kink in the graph. The derivative is dne. So we don't want there to be a y value at 3 because there's not supposed to be a derivative at 3. So the easiest way to show that is just to put an open circle on each of those two endpoints to make sure that we don't include either one. So this would be my graph right here. Okay, this is the graph of my derivative. And since this was position, the derivative of position is velocity. Okay? Now in this next example, we're going to do the same thing but in the opposite direction. So this time I'm giving you the velocity, I'm giving you the derivative graph already, and I want you to think in reverse about what that position function must look like in order to guarantee that its derivative graph will be this. Okay? So if we think about our previous example for a moment, remember that 0 slopes on the velocity, or 0 y values on the velocity corresponded to 0 slopes on our position. So right here, I have a 0 slope because that y value on that derivative is 0. So over here on my graph, I need to have a 0 slope. And that usually happens when I have a maximum or a minimum showing up in my graph. So we need to see either a max or a min happening at 2. Now on the left side of 2, all of these slopes are positive slopes. And when you have positive slopes, that means your graph needs to be rising up and getting bigger and bigger and bigger and bigger, since these are getting more and more steep, getting larger and larger and larger. So those slopes, those tangent line slopes, are getting more and more steep as we progress towards 0. So we need to have positive slopes on the left side of our 0 slope, and down here we need to have negative slopes to the right side of our 0 slope at 2. So how could we put this together so that we have a graph that is sort of rising up and then levels out to 0 and then falls? It would have to have that kind of shape to it. And I don't know exactly where that's going to be over here. It could be up high, it could be down low. We don't have enough information to know that exactly, but we can just give a rough sketch that has this shape, so that if I rise up and have a positive slope all the way up to 2, and then I reach my peak, and then I start falling again back down to 3. So if I had a graph that looked something like this, would the tangent lines to this have slopes that would give me back this velocity? Sure, because here's that 0 slope. These are all those positives that are getting bigger and steeper as I go to the left. And then these are all negative slopes getting steeper as I go to the right. So this graph right here in blue would be a good sketch of what our position function probably looks like in order to guarantee that it would have this velocity graph. Okay, so that's kind of tricky going backwards. All right, our very last example. We want to find the volume of a cube with the sides of length s is given by this formula, v equals s cubed. We want to find the rate of change of the volume with respect to s when s equals 4 centimeters. Now, rate of change in calculus, rate of change, and I don't see that word average, so instantaneous is implied. An instantaneous rate of change always implies derivative. So we want to find the derivative of volume with respect to this side length s. So we're looking for the derivative of volume. So we're looking for v prime. And since the variable that's given in this formula for the volume is s, we're taking the derivative with respect to that s variable. So what would be the formula for this derivative function? What is the derivative of s cubed? Well, it's a power, right? We bring down the 3 and we subtract 1 from the power. So v prime in general is 3s squared. So what would v prime be when s is specifically 4? Well, we just have to plug in 4 for s. So if we substitute in 4, 4 squared is 16. 16 times 3 would be 48. So our volume, rate of change of our volume with respect to the side length would be 48. Okay, let's stop our lecture here on basic differentiation rules and rates of change. Good luck.